Memory safety is a confusing topic, and I see a lot of people get confused by it, especially this statistic right here and how it's used. So, what do you think is wrong with this statement here? 70% of all CVEs are from memory unsafety. C is memory unsafe, so 70% of CVEs will be from memory unsafety. Zig is memory unsafe, so 70% of CVEs will be from memory unsafety. What is wrong with this sentence / comparison here? I'll give you 3 seconds, and obviously you can pause if you want longer. 3, 2, 1. The predominant issues are these four right here. We're number one, applying a percentage wrong, and then also it's a percentage. And then we also have the question of what is memory safety and what is memory unsafety. Those are very important. So let's sort of start with this applying like a percentage wrong. Number one, this percentage is comparing all, like basically most, I think all CVEs, but basically it's the industry standard for CVEs that 70% of the CVEs for basically any company is going to be roughly 70%. We can see here 65% for Android, 66% here, 71% for iOS, macOS projects, Chromium 70%, Microsoft 70%, Firefox CSS subsystem 73%, Ubuntu Linux kernel 65%. Basically every single one is like roughly 70-ish percent. Like, yeah, this is basically the industry average. So that percentage, however, is not talking about C, it's talking about the CVEs. And the CVEs are actually measuring C. So in this case, this will be accurate, but again, it's not measuring memory unsafety. It's actually measuring the memory unsafety in C. It's specifically talking about C and C++ code bases because that's the majority of all code bases. The memory unsafety is different in Zig than it is in C. These are not the same as well. So we're applying a percentage wrong in this C example, and this is sort of an insidious example because it's technically true because the CVEs are C code, but then on top of that, when we do that and then compare the 70% to Zig, and we're comparing Zig's memory unsafety to C, this is also inaccurate because they have different memory unsafety profiles. Like they're very, very different in terms of their unsafety and how much unsafety they allow for and what their guarantees are. So that's also going to be wrong because we don't know what the definition of memory safety or memory unsafety is in this situation here. So first, let's actually just discuss the percentage because, like, obviously the percentage is talking about the code base on average, and we can sort of just get the example, ignore this part, but yeah, this is roughly the time period here in terms of the 70% for Google. And I mean, even they sort of just admit that whenever they first started doing like programming, they were just programming, right? They were just throwing code at the wall, programming as fast as possible, and just trying to get stuff done quickly, right? They're about features. They weren't necessarily trying to write, the safest code in the universe. So they were reactively patching problems. They were trying to make their code, not horrible. They're trying to do a good job. But if there was a memory vulnerability, they would fix it after it's been found. And that's like a relatively reasonable approach. People do it a lot. So it's not like I can say it's unreasonable because there's a lot of reasonable people that do this approach, but it's not great. But the third approach is obviously going to be a lot better, which is using sanitizers and fuzzers and actually looking for vulnerabilities ahead of time, like actually looking for the vulnerabilities and trying to fix it. Obviously, this is probably not going to be the 70%. Like actually going ahead and making your code safer and trying to be safer is obviously going to make your code a lot safer. Like actually trying is going to make your code safer. So again, the 70% is the average across the industry. It's not for a specific code base. It's not for your company. For example, it's not for my company. It's not for my code. It's for the code on average, which is still important, but it's the code on average. It's something important to remember because there are projects by NASA and other projects that have guaranteed safety. You can't actually make C verifiably safe. There are code verifiers for C to guarantee safety for writing projects like for NASA, for example. And they have a lot of static analyzers and they have a lot of rules that make sure that you can't make like a mistake basically and do something that could even ever have an error, including even allocating memory. You're not even allowed to allocate memory on some of those things. They have very strict requirements. So hopefully that makes sense that it's a percentage talking about the average code base, not safe code bases, the average code base. If you're trying to, write safe code, how good is your percentage going to be compared to like NASA? Probably not as good, but it will probably be better than 70%. Now, in terms of memory safety and memory unsafety, that's where we get into the next part, which is important to keep in mind, which is the fact that these errors are basically, we have like these three major errors here. But let's go to the Wikipedia page to actually like look at it. So on the Wikipedia page, they mentioned, there's spatial and temporal, and there's buffer overflow, buffer overread. Both of these are basically just going out of the bounds. Yeah, out of bounds writes and out of bounds reads. I combine those into one problem. And then we also have uninitialized variables, which can cause wild pointers, invalid freeze, and also just a lot of other bugs. Like uninitialized memory is like really bad. It will cause a bug that is very hard to find very quickly. But yeah, so those two are the main ones. Then the rest is like mismatch free, double free, useset free. This right here is a data race, which I don't really know why it's in here. It's a very specific thing, and it's normally not added to the list. I don't even think Rust people mention this as a thing. Apparently, like they say, like the Rust programming language right here, it prevents this kind of memory-based race condition, but it's like, it's a race condition. By definition, it's like mutating memory. It just seems like they're trying to add it to memory safety to try to say that they're more safe than like other stuff, but it's like, I don't know if it's necessarily a memory vulnerability. It's a multi-thread problem. So I personally don't count this, and I don't know, like, I don't know. I could see there being an argument, but it's a little bit weird, so we're going to ignore that bottom one there. So the main thing is these freeze, uninitialized, and buffer overflows. So we have the basically three main categories of memory safety. Now there's obviously like more specific categories that we can talk about as well. So for example, you can return a pointer to stack allocated memory. So this kind of error right here is specifically a use after free. However, it's a specific kind of use after free. So that's an example where we could have more specific genres within each of these, but typically we have these three major categories. So hopefully that makes some amount of sense for that. Out of bounds is trivial to fix. Even in assembly, you can actually fix this if you make your own standard library. Because the biggest problem is just having data structures that aren't bound by a length. And even if you just make your own standard library, you can fix the like 99% of that yourself. But granted, most languages actually just have that by default. So Odin, D, C3, Zig, FilC, and more languages, almost all modern languages, have bounds checking by default. Uninitialized memory is another one that is fixed in Odin, D, C3, Zig, and FilC. And then obviously for D and FilC, they also fix the third error as well, because both of these have a GC. Now D has an optional GC, so you don't have to fix this error. You get to decide whether or not you want to have the use after free possibilities or not. So D is a little bit different than FilC, because FilC is always garbage collected at the moment. Apparently there's a way you can fix that, but that's beside the point. So yeah, when you're looking at modern languages and you're comparing them, you cannot compare that 70% because you have to basically remove the bounds checking and uninitialized memory, and you probably should also remove the stack pointer one as well. But at the same time, because most of them, like, I don't know how many of them fix it, well, we're going to leave that off. But there are some other things that they fix related to use after freeze and different things that they analyze. Like, obviously, Odin and Zig, and I think C3, but Odin and Zig have debug allocators, which allow you to try to look for those use after freeze a little bit easier, and sanitizers and stuff like that. So there's some things that you can do to, like, make it less likely to make use after free bugs, and there might be some other guarantees. So you need to subtract off of the use after freeze a little bit more than this, but we definitely should not be looking at the 70%. Like, if you're saying that, like, oh, like this statement up at the top, right, like what we sort of discussed, Zig memory safety, you need to subtract that that number. So what is that number for that? So let's actually go down and we'll sort of discuss that. But first, just actually, I was going to use this as examples, and I forgot to. But this right here is the use after free. So yeah, you allocate memory, then you free it, and then you try to use it. This right here is out of bounds. So you have an array of 10 values. You try to access it past that bounds. It would also be the same if you try to go negative and you try to access that thing. It's out of bounds. This is uninitialized memory. If you try to print this out, it'll give you basically a random value. So those are basically the three categories of errors, and this is the predominant one that is actually a problem. These two are fixed by like I said, every modern language has these two main issues fixed. Now, that does mean if we actually go check and look at Chromium, 36.1% are from use after freeze, and we go to the Android one here. This one, I could not find the percentages, unfortunately. There might be percentages out there somewhere, but I could not find them, so that's a little bit unfortunate, but we're just going to have to stick with this here. Out of bounds write, out of bounds read is almost 70%. When we take in the uninitialized, it's really close to 75%. I don't know exactly, but it's pretty close, and then it's slightly tilted. Let's just say it's around 12-ish for the use after freeze. I think that's pretty close because this cuts it in half almost exactly. I think it could be slightly less than 12, maybe. I don't know exactly. So let's just say around 12-ish, and then let's just take an average between the two, which would be about 25% use after freeze. So whenever you're comparing these languages, we're going to have to use this 25%. So you can say Zig is memory. We could say like a different statement like Zig is memory unsafe. Actually, yeah, that's sort of difficult because it's not memory safety anymore, right? We're talking about use after freeze. Zig's protections are limited. So 25% of CVEs will be from use after free. That is a statement that we could actually say with relative accuracy. Obviously, we don't know the exact statistic, unfortunately. And that's sort of the problem with a lot of these stats. They are talking about like code sort of on average across a lot of different things, and they're not really talking about the specific memory unsafety. And especially when we look at something like Android, right? That could potentially be like 70%, 75% of all the memory unsafety could literally be from two things that are trivially fixed by Zig and Odin. So depending on like your code base, depending on how you're writing the code, very well you could end up with 12, 36, or just 25% use after freeze in terms of the actual errors. So yeah, that's something to keep keep in mind with this, right? When it comes to memory safety. So whenever you're saying that like, oh, Rust is better than like Zig, for example, or Odin, or C3 or whatever, right? If we're actually going to sort of try to make this a comparison, we can only say that like we can't say that Rust is 70% better than Zig, right? We cannot say that. We can say that Rust is 25% safer than Zig, right? We can say it's 25% safer than these languages on average. Obviously, that's also not necessarily true, right? Because, like I said, this is a percentage, and specifically, we're talking about the guarantees of use after free, not just memory unsafety anymore, not just C. We're not just talking about code bases in general. We're talking about Zig code bases, Odin code bases, and C3, and like the standard way that you're supposed to write those. Because, I mean, again, with C and C++, they don't protect you from a lot of really dumb mistakes, and these languages try to protect you from a lot of those. So there's two important facts we need to understand about use after free on top of that. So number one, you must allocate memory first before you can have a use after free. You also must free the memory before you can have a use after free. So those are two things you have to do first. You must allocate memory, then you must free that memory, then you must use that memory. This is extremely important to keep in mind, specifically because you can avoid both of those. If you don't allocate memory, then you're not going to have a use after free. And there's a lot of situations where you can avoid allocating memory. But if you allocate memory and then you just never free it, then you can also avoid a use after free. And there are some circumstances like that, and it's important to keep this in your head. Also, if you decrease the amount of allocations that you have, so if you take your allocations from like if you take your allocations from 10 allocations down to like 1, I don't know if that's going to be a 10x increase, right? I could see there being an argument for being a 10x increase. I don't really know. The problem is you could obviously have more use after freeze than you do allocations, and you get more use after freeze than you do freeze, right? You can have an unlimited amount. You can just keep writing the use after free, right? You can just copy paste the code, but you're drastically less likely to have a use after free for every time you decrease an allocation. So if you're able to decrease an allocation and decrease a free, especially, if you ever decrease the amount of frees that you have, you're drastically less likely to have use after free problems. Now, is that direct? I would say it is proportional to the amount of frees that you have and the amount of allocations that you have. However, I don't know the exact stat on that. Is it going to be, for every 10 allocations or for every 10 frees that you decrease, are you going to actually get like a 10x improvement? So is it like 1-to-1 proportional? I don't really know. Is it like 2-to-1, right? There's sort of a stat here, like we don't really know what it is, but there's definitely some stat that we could look at, and it probably is proportional, probably not 10x. there's probably, like I said, there's some sort of percentage of decrease. So if you decrease the amount of allocations you have, you're going to decrease the amount of use after freeze if you have. And if you decrease the amount of freeze that you have, you're also going to decrease the amount of use after freeze that you have. So those are two important metrics that you can decrease, which is the allocations and decrease the freeze. And if you decrease both of those, you're able to decrease the amount of memory vulnerabilities that you can possibly have, which is very important. Now, the second thing to sort of keep in mind is that use after free is a malloc problem and not an operating system problem. This is a little bit of a weird one because people don't really think about this, but use after free is only a problem because of malloc and not because of the operating system. If you use virtual alloc or if you use memmap, which is how you call the operating system to grab memory, it's a more limited interface. But yeah, if you allocate memory using the operating system and then you free that memory, you'll actually get a access violation. That is really important. It's basically a null pointer dereference. And the reason that that is important is that means the operating system doesn't have a problem tracking the memory. The only reason that you don't do this is because the operating system is slow in terms of allocating memory. But because we know it's a malloc problem, we can actually fix quite a bit of this. So in terms of like using an arena and using an arena to group allocations together, number one, that's going to decrease the likelihood of having like problems. You can do that with like an arena very easily. But then on top of that, if you use an arena to do a bunch of allocations and you free all, you can have a use after free bug. But then if you do an arena delete and you give it back to the operating system, you'll have an access violation instead. So you can actually create safe arenas that are completely memory safe if you replace free all with delete. Now, obviously that is slow. So you can, like I said, make arenas actually completely memory safe. By the way, you can make them, or may not completely, I don't know. I haven't verified that. I wouldn't necessarily say that it's verifiably. So I can't think of a single situation that if you made free all delete instead, where you would end up with a issue because you just deleted it completely, gave it back to operating system, you're going to have an access violation instead. So yeah, like it should be completely safe. I can't think of a single way that you get around it. Now there might be, so comment down below if you know of a way of getting around the operating system like this, but this should make an arena safe. So keep that in mind. Also, because it's a malloc kind of thing, you can also create your own generational memory manager, and you can just have a generation and an index, or a generation and a pointer, and you can actually make a safe allocator, especially for specific allocations. So you can have a struct or like an entity or some sort of group of things, and you can make an allocator specific to those group of things. So you can say like spawn entity or whatever in your video game, and whenever it grabs a new entity, it gets it off the free list, and it uses this generational index basically to verify that like, oh, the generation is equal to the value that's actually being stored there, so I can't accidentally mess that up. And I think there's probably a way to do this with arenas. I've never actually done that before, but I could see where if you do free all, you can increase the value of the generation of the arena. So you could have a arena with a generation, so that if you try to access a value that was in a different iteration of this arena, that doesn't let you anymore. So that's probably also possible to make a generational arena. So there's definitely a lot of things that you can do to make arenas and other allocators way safer if you want to do that, right? It's an issue with malloc, not necessarily with like this. And like a good example of this is garbage collection. Garbage collection is sort of like an allocator, and it's obviously a safe allocator. So you can just make your own allocators that have safety features built in. The same thing with like the debug allocator having safety features built in. That's sort of another example of this. So you can just make allocators that are a little bit safer. So again, a lot of people don't seem to sort of understand this, unfortunately. And I see a lot of people basically have the sentiment, this is sort of funny, but basically people just compare like C, Rust, and like TypeScript. Those are the only like 3 programming languages that exist, and it's just really quite hilarious in terms of the way people sort of do that. And the same thing with like the comparison of like the 70%, right? Where they're basically saying like Zig is like worse than Rust because Rust protects you from 70%, while Zig doesn't protect you from those issues because Zig is memory unsafe. And it's like, yes, Zig is memory unsafe because it allows you to write memory unsafe code. That's how Rust defines it. But Rust also allows you to write memory unsafe code. Their definition doesn't even count Rust in terms of being memory unsafe. That's why I don't like the definition of like Rust's memory safety model, right? You can say Rust is memory safe by default. That's actually a better thing. So for example, like the D programming language is not actually memory safe by default, but you can absolutely make it memory safe. D is just as memory safe as Rust if you just turn on just the safety features. Like you just turn it on, and then it's just as safe as Rust in that case. You just have to turn it on. It's not safe by default, but it is just as safe as Rust if you turn on like one flag, basically. Actually, I think it's specifically to get the full features, you have to turn on 2. One of them is slightly experimental at the moment. But yeah, that's a good example where D is technically just as memory safe as Rust, but it uses a GC. The same thing with like Java, C Sharp. They're all just as safe as Rust. They're all memory safe, right? They all protect you from those issues. So it's important to keep this in mind, that that percentage, number one, is protecting you from specifically use after freeze. And the same thing with garbage collection. Garbage collection only protects you from use after freeze. And the same thing with FilC, same thing with Rust, same thing with any complex programming language that tries to protect you in terms of memory safety. The only one that's actually unique in terms of like needing to be solved is use after free. And that is what Rust protects you from. That is what garbage collection protects you from. That is what automatic reference counting protects you from. That's what all these different things protect you from, is use after free. Because the other two are fixed by very easy means. The only other thing is literally just use after free, which is 25% of the issues. And if you're using an arena, that's going to be way less. If you're using a sanitizer and a fuzzer, it's going to be way less. If you're using the arena and actually deleting it, giving it back to the operating system, it's going to be way less on top of that. So yeah, if you're actually like doing good practices on top of using a decent programming language that has these two things fixed, or if you built your own safety measures in with C, you can get that number way, 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 way down. So again, 25% probably on average, according to the two Google code bases. It could be higher, it could be lower. I don't exactly know. I want to see some stats on this. If you do know, send a comment. But yeah, hopefully this helps you understand like memory safety a little bit better. That it is predominantly those three issues. All two of those issues are actually fixed, and only one of them is a real problem. And that problem is actually only 25% of the actual CVEs, as far as I can find. So anyway, hopefully this helps you out. Have a great, wonderful, sublime day, and God bless.